Hey everyone, this video will be about the Ukkonen's algorithm for linear time and online, not just linear time, plus online, suffix tree construction. Now, I think before we actually could dive into the algorithm, it's best to compare the suffix tree construction algorithms types. So what I mean by this is you have the naive suffix tree construction, which is O of n squared, versus the linear time, which is Ukkonen's, and try to find the differences between them. So for the naive algorithm, what you're really doing is you just construct the entire tree. The idea is construct tree by adding suffixes from longest to shortest. So you might start by adding the longest suffix, which would be actually, before this, I do want to mention we're going to use the compact edge representation. Sorry, compact substring representation. Instead of storing the entire substring, we just store simply just the start and end of this substring. So you might add. So back to my point, you might add the first link, and you might be like, oh well, this goes from the first character to the, let's say this is nth character. And then you might add the second substring, which is from 2 to n, and you might have need to create, and there might be a partial match between them. So this might be 1 to 3 and 4 to n, and then this will be 5 to n. Right? So you just create it, just keep adding suffixes that are progressively like shorter. And this is still a pretty good method. It's O of n squared in the worst case. The worst case would be something like a n times. That's right, so that's this. For Ukkonen's, it's gonna be where we built it in phases, and each phase we're building the suffix tree. So in the ith phase, so you're gonna have n phases for the n characters. In the ith phase, we construct suffix tree for first to the ith character of these strings. Suffix tree just for this substring 1 to I. So you're really just incrementally increasing it. And while initially this might seem like, oh, well, that doesn't seem that efficient, because you have to, let's say character string is A, B, A, say the string's banana. And then in the third phase, you build the substring of just BAN, so that's got BAN, A. Sorry, the suffixes you're working with is N, A. So you got 3 suffixes. And then now you got to add 4 suffixes to all of these. So you're doing sort of, you might think you're doing n minus I steps of work, n minus I iterations basically. Suffix additions per iteration. this will, if you add them all up, you'll sum up, I think, n times n plus 1 over 2 iterations. So, and then, you might, if it was just typical addition, each addition can be O of n, so it could be n cubed, just by your initial look, because really here you only add n suffixes, and the worst case can have those n form an n squared, right? Okay, times by n. N suffixes lead to n squared. Similar logic would mean that n squared suffixes basically could be n cubed, or at least a bad n squared, because even the number of steps seems quadratic. I mean, we have no idea whether each step is linear. But there's some key observations that make this actually linear as you average it out across the thing. In particular, we don't, for each ith phase, we don't just go through each substring, or like, n minus I substring, so that will definitely be quadratic. Instead, we use shortcuts. And this is not the most simple shortcut, but essentially use prior information, or like prior information from the previous phase, in the current phase. And what I mean by this is, let's say we have the current phase being so we add this string for banana. Let's say we've added the first. So banana, if you add the first, after the first addition, would just be, you just add b. So from banana, the root would be 1, 1 like this. Then after the second addition, might be 1, 2, because this prefix becomes 1, 2. Sorry, the suffix becomes BA. So it goes from B to BA and A, and you might need to add another one for A. So there's 2, 2. And essentially the key idea is, there's a lot of key ideas actually. And you have a few optimizations to help you with this. But before we do optimizations, let's look at the key ideas, observations that help us with this. Here's the key observations. Each addition can follow one of these three rules. Rule 1 means you extend a leaf. Essentially, if you take a look here, take a look at this leaf here. Actually, let's add banana. Let's add the character n. So n and n. This is the new addition. And look what we have. We are extending a leaf. We go from BA to BAN. Basically, we have BA, and we just extend n. So really, we're just making this leaf longer, the part of the leaf longer. Yeah, extending the leaf is, I guess, the best way to say it. That's probably why it's named that. So leaf extension. And turns out all of this can be done in O1 space for all leaves, which we'll get to soon, but for all leaves, not per leaf, for all leaves. And rule 2 is when you, then we'll see this here, is when we add n, and here's also extending from 2, 2 to 2, 3, because you go from a to an. And then rule 2 is when you have to create a new leaf, create a new branch, sorry. Right, so rule 2 is when you create a new branch. Well, if you observe here, n has not occurred yet, so you have to create this new branch. And rule 3 is actually when suffix is in a branch already fully. And the key observation to make here would be not a good example of this is when you add a. Notice how bana, that's rule 1. You go just extend this. Same with ana, 2, 4, and same with na. It's just extending this. But a, just adding a, it's already part of this first thing. Oh no, that's also rule 2, sorry. No, sorry, yeah, it's already part of this ana. Therefore, you do nothing. So realistically, the only work you do is when you create a new branch. Now, this seems pretty good. But before that, let's talk about, and yeah, even when doing this work, there's some tricks to optimize. There's some optimization tricks here for sure. Okay, so first let's discuss how we can make leaf extension all O of 1. So O of 1 for all leaves. So here is some ideas behind this. There's some observations we've got to make here as well. This is quite a complex algorithm, so we have to make observations for basically each part. The observation you have to make is the fact that something is, if it's once a leaf, always a leaf. If it was originally created as a leaf, it will remain a leaf. Right? So that means you can, if you set something to be a leaf initially, that will be a leaf forever. So if hypothetically there was a leaf, there was a trick to extend leaves very quickly, this probably helps out because you can keep track of all the leaves, because once you create a leaf, that will be a leaf forever. And that's the only way we have leaves, because we're starting from scratch. And secondly, another observation is, if something was rule 1, so if I need to use some terminology. Let's introduce a new terminology. Within each phase, there's an extension. Within the ith phase, there's I extensions. Right, so in the fourth phase, we had 4 extensions. Extension 1, where we extended ban to banao, and extension 2, and extension 3, and extension 4. And the key observation is, if extension J was rule 1 in phase 1, it was, sorry, rule J, rule 1 in phase I, it will be rule 1 in phase J as well, sorry, I plus 1 as well, the next phase. So what it's saying is, if it was, whenever it becomes rule 1, whenever something is rule 1, it will stay rule 1 forever. So, so we know that this was rule 1 from the second phase onwards, so it will remain at rule 1 forever, the rest of the string. So that is the key observation. Now, why is this? That's actually a great question. Well, the reason why this is true is because let's say we have a string that's, we have a suffix tree, and we know something's rule 1, meaning that it's got a perfect match down this path till the very end. And that perfect match hits a leaf, right? So that means path from string 1 to, or not 1, it could be anything, it could be I, some J to I is just a leaf. And then by J to I minus 1, sorry, because we're in the I, wait. If we're in the ith phase, J to I minus 1. Okay, so this is the ith phase. This is the formal representation of rule 1. And then we make so that string, what we do is we add a leaf, so the string J to I is a leaf. Read as a leaf. Because there might be other nodes in between. What I mean by this is, you start at J here, and then you reach I, but there could be like other nodes in between. We don't know that. But the point is, the path in the end will reach a leaf. And therefore, in the I plus 1 phase, look at the implication. If we just try to match J to I plus 1, J to I will reach a leaf, so that means the I plus 1th character won't be found because you're at a leaf. You can't go any further down, so you add leaf. Only thing you can do is add a leaf. Therefore, it's rule 1 because you're extending the leaf, and then it means string of J to I plus 1 reaches a leaf. Is a leaf, not reaches a leaf, is a leaf. The path to a leaf. Say it that way. That's the logic there. So now, why are these observations important? These observations together mean that every time we get a new rule, the amount of work we have to do decreases, because you go from rule 1 all the way to rule 2, and you don't need to do work till you reach rule 2. And let's say there's 2, that means no need to recalculate No need to do any work for rule ones in future phases. So if something is a rule 1 in current phase, it will remain a rule 1 in the future phase, so you don't need to do any work. And as a result, and you know what these are, and you know what the rule 1s are, because you'll just have a bunch of them at the start. So what you can do is you can just predictably use a global end variable. So instead of incrementing every single thing leaf by 1, the end of each leaf by 1, you use a global end variable and increment that by 1 for the leaves. Now that is the first optimization. So that means you can extend it without any work, and this is called a rapid leaf extension. That's the first optimization. Now and that'll be it for today's video, but I'll do a quick overview of like what's to come. We also need to talk about rules to create a new branch. So optimizations to creating a new branch. Something called skip count. We also use suffix links, and this which we'll get to later, and also this idea called active nodes, or active something, which includes, let's just say active nodes for now. But yeah, that is the there's some activations we can make for the actual work as well to make it linear. Well, as we can see, we can already cut down a fair bit of work by this idea. And the way we'll implement this is in 2 ways. We'll have this thing called a remainder, which is basically the number of non-rule 1 nodes or extensions, or like your characters left, and because all the rule 1 stuff you can just ignore and just do the rapid leaf extension as we talked about. But yeah, we'll get to the other optimization soon, but that's the first video on Ukkonen's algorithm.